Our next speaker is Sergio from OneSpin Solutions. Sergio is a technical marketing manager at OneSpin Solutions and has over 20 years experience in electronic chip design and deployment of advanced hardware development solutions. His expertise covers IC design, functional verification, safety standards, including ISO 26262 and DO254, and detection of hardware trojans and security vulnerabilities. He is passionate about enabling the next generation of high-integrity chips that underpin the Internet of Things, 5G, artificial intelligence, and autonomous vehicles. Thank you, Sergio.
Hi, everyone. Thanks for being present here at DVClub. So I'm going to talk to you about IP verification, IP integration verification challenges, particularly in large SoCs. And in particular, we will look at the connectivity verification challenge, which we solved together with Xilinx. So one slide about OneSpin. OneSpin provides certified IC integrity verification solutions to develop functionally correct, safe, secure, and trusted integrated circuits. So what we mean by IC integrity is really made up by three pillars: functional correctness, looking for bugs, proving bug absence during pre-silicon verification; safety, which is about ensuring that the hardware is tolerant to faults and deriving hardware safety metrics and comply with the safety standards; and trust and security, which is about ensuring that the hardware really does not do anything that it's not supposed to do, whether it's through misuse case scenario, through security vulnerabilities, weaknesses, or even through malicious logic or hardware trojans. The focus of this presentation is on functional correctness. So if we look at modern chips for AI application of 5G or even automotive these days, the size of the SoCs that are used is increasing dramatically. That's why we talk about extra large SoCs. And one critical task is IP integration verification, even subsystem integration verification, which, especially due to the size of these chips, becomes a complex and time-consuming task. So in the connectivity verification task, we typically have a source signal and the destination signal, which may be deep down through to many hierarchy levels and many signals in between. And we want to make sure that the source and destination are connected. This is to verify, for example, that the bus wiring that can go through many layers or a hierarchy is correct, that the use of I/O pads, which can be highly configurable, is correct. And in this case, we have a connection that really depends on how the hardware is configured at that time. Obviously, we have lots of IP blocks, analog blocks within the SoC that needs to be wired up. There is also the problem of checking that the routing of global signals is correct, like clock, reset, debug, and scan enable. And depending on how your SoC integration flow works, you may have also some automated insertion of delays in this spot, like registers, for example, for timing reasons. Now, what are the issues with verification? Well, first of all, even simple connectivity bugs can waste much effort. Probably they will be found as soon as a few tests are run in simulation, for example. But because you are dealing with a large chip, it's still going to take a while to run the test, debug it, and even a simple bug is going to waste significant effort. Another issue is the specification, because when you actually have thousands, hundreds of thousands of connections to specify Obviously, first of all, there is this effort to generate the specification, and then with this large number, there is a high likelihood of making mistakes. And finally, obviously, the worst of all, probably, the risk of missing a bug. You can have connections that are only active or significant in some corner cases, which means that you may actually miss wrong connections. And that obviously would be a very serious bug if it reaches silicon. So how do we address this challenge, or in the past few years? Formal connectivity checking has been quite successful in addressing this challenge in the past. It's kind of a sweet spot application for formal. The way let's say traditional formal connectivity checking flow works is that the engineers develop or reuse a connectivity spec, and they obviously need the model of the design, typically the RTL. This is compiled into a formal tool, and then a formal tool typically automatically generates from the connectivity spec a set of assertions that are proven on the design. And either they are proven through exhaustive proof, hopefully. Ideally, you don't have obviously bounded proofs, and or if there are fails, you get the debugging. When you prove assertion, you actually prove that, for example, you can prove that two signals always have the same value, but that doesn't really mean that there is a physical connection between the two signals. So let's say good connectivity checking up, like for example the one from OneSpin, include the structural analysis check as well, which really look at the presence of the physical connection. So in summary, we have a detailed connectivity spec that is used. The assertions are generated automatically and hopefully exhaustively proven. And in addition, we have this structural analysis to ensure the physical connection between source and destination signal. Now, if we look at the traditional connectivity checking spec, we have a source, a destination signal, possibly some delay, either fixed delay or range delay, possibly some conditions where the connection is really active under a certain configuration of the chip. And typically we are going to have also multiple clocks, so you might have to associate the clock to a connectivity spec. So you're going to have like one of these entry for each connection. You can have several forms to express that, but ultimately it's like this type of table. Now, of course, another problem here is that you have to create and maintain, this for a very large number of connections typically. And when you have many connections in a complex chip, you can run into also complexity issues because runtime is too long, proofs don't converge. So here we really have two problems really. Specifying all this connection, maintaining all this connection while your project develops, and then proving this, and dealing with complexity issues. So let's look at Xilinx case study. Xilinx had several challenges with connectivity checking in their project. They had multi-billion gate SoC on 7nm technology. To give you more sense of the complexity, there are some other numbers here, 35K modules, 60 million instances relevant for connectivity checking, 90 million flops, and 80K FSM. And they wanted to specify and prove in excess of 1 million connections. Obviously, design schedule is tight, no surprise it was tight, no surprises there. But they still didn't want to compromise on quality. They wanted exhaustive proof. And so they tried a range of connectivity checking app from various vendors, including the, let's say, traditional connectivity checking app from OneSpin, but also others, and they were all unsuccessful. They had excessive runtime, inconclusive results, and they really have having too much effort to deal with so many connections. So OneSpin partnered with Xilinx to address this challenge, and we developed a new next generation connectivity checking app, which we call Connectivity Excel. And what are the flow? What is the flow using this app? So in this case, the user needs only to specify an abstract connectivity spec, which we'll see in more detail later. And of course, the user also needs to provide the model of the chip, the RTL. And then what the app will do after compilation is to actually automatically expand the abstract connectivity spec into a detailed spec. So this step is totally automated. And in addition, the app includes dedicated proof engine to deal with complexity in this specific type of problem. And also I'll tell a bit more about this in a minute. And of course, what comes out is either an exhaustive proof, and here the goal is really to get exhaustive proof and not bounded, proof results, inconclusive proof, and also debug information that can also deal with very complex path, and enable quick debugging and root cause analysis of any fail. So a little bit more about the under the hood technology that powers the app. So the app really what it does is to merge the structure analysis and the formal proof checks. And this allows for a number of optimization. It allows for more advanced and automated abstractions. It also allows to localize the proof to the minimum logic required, let's say, because typically the complexity comes from proof engines. And also it enables, to kind of stop analysis as soon as an issue is identified. So typically when you have a lot of connection, you're going to have a lot of checks running in parallel, and some checks, queuing for a free slot, and the sooner you can free a slot for the other checks that are queuing, the faster will be your overall proof. So digging in on the other aspect, the crucial aspect, the abstract spec. Here we can see an example. We have again a table and source of destinations, but in this case, instead of providing just signal, the user can even reference, module of instance signals. It can use wildcards in the names, and it can also omit delays, change of polarity, multiplexing conditions. And this will all be, let's say, automatically handled by the tool. So in this way, basically, you get much less entries and much simpler entries in your connectivity spec. And the tool can automate a lot of the work to generate the detailed spec. And in addition, the app is also customizable, and you can leverage, for example, coding guidelines to do additional checks or to directly leverage this into your specification, connectivity specification. So what results did Xilinx got? So first of all, they were able to detect several corner case bugs, with the incorrect block integration. They also reported, detecting issue due to multiple drivers in the record venture paths. And they were also quite pleased with the debug, and they, for example, reported the case where there was a signal path with a connectivity path which involved 2,000 in the order of 2,000 signals. So of course that can be quite tedious to verify in general, but through our specific debug support, the debug was quite quick, because basically the tool points you to the exact point where the problem is. And They also minimized the risk of missing bugs, first of all, because they didn't get any inconclusive proof, so they were able to exhaustively prove all the checks out of the box, and they were able to do this for over 1 million connections within days, let's say, using parallel jobs, which was sufficient for them. In terms of the apps of specification, you know, they were able to reduce a lot the effort to create and maintain the specification, because through this apps specification, basically, they reported roughly 100x compression factor. So this means that the user had to deal with a much more compact specification, and so yeah, this saves a lot of time. In addition to being more compact, the specification, it was also, the entries were simpler because the tool were able to automatically handle, you know, conditional connectivity, delay flops, inverters. So they, for example, didn't have to maintain all these things during design iteration. Finally, what they also reported, which was news also to us, we hadn't talked about it, was that they were able to do a lot of quick iteration when modifying the connectivity checks, because basically the way the flow works, you don't need to recompile the design. You just need to elaborate the design once, and this means, you know, especially when you deal with large SoC, you know, you save basically a lot of time there. So in summary, Connectivity Excel successfully addressed Xilinx connectivity challenges and, you know, overcome all the limitations from traditional formal connectivity checking. They were able to use the abstract connectivity spec and automatically generate a detailed spec. They were able to leverage, you know, this under the hood proof localization algorithm to get, you know, huge speed up in runtime and capacity. And ultimately, they proved over 1 million complex connection in their 7-nanometer chip. And this case study is also, say, more information is in a paper that was presented at the DVClub conference, authored by Xilinx and the OneSpin engineers. And you can download it from OneSpin website, onespin.com resources, conference-materials. And I believe you will also receive an email from TVS with a link to this content. Thanks a lot for your attention. I hope you found it interesting. Bye.